Hello. So this is a topic that I've wanted to do a much more elaborate video on, just on the general subject of audio synthesis and especially focusing on additive synthesis. But I don't know when that's going to happen, so just consider this some sort of crash course on the subject, just going over one specific example of code that I wrote a while back. This is specifically for the 2T22 no reverb simulation, and so you'll get to see how I did that. So the code is linked in the description if you want to follow along, or if you want to experiment with it, or whatever you want to do. Otherwise, I'll try to get through this, look at what I wrote and try to remember why I wrote it and stuff like that. If you're a programmer, you know what I'm talking about. Ideally, I wanted to rewrite this in like Python or something that more people would be familiar with, but one of the things I always run into an issue with is working with binary files. I mean, I'm sure it's not difficult and that it's possible. I just never really bothered learning how to do that. It's a C program. We have to include our header files. Standard input out, that is for writing to a file. Math is for the sine function and the exponential function. Standard lib, I think that's just for the random function that I'm using a little later, and then time, that's for seeding the random function. Keeping track of a few constants, 2 pi for the sine function, and then the sample rate, 48 kilohertz, that's pretty standard. Length, that's the length in seconds that this file will end up being. Frequency, this is essentially the motor frequency in hertz. So multiplied by 60 would give you the RPM. And then the harmonics, that's how many harmonics we're going to generate in the sound. The more harmonics, the more realistic the sound will be, but it's also going to take longer to generate, so just a trade-off there. Now, this current frequency function, we give it the current time in seconds that we're at, and it returns what the frequency should be at that time. So basically, the first 10 seconds, it's just going to do a constant, I guess the full RPM sound. That's just to kind of judge to make sure we've got the harmonics correct and all that before generating the entire, 4-minute and 10-second sound. We're relying heavily on the exponential function to give us a realistic sounding wind up and wind down. And the reason for that is it gives us a smoother transition from the wind up to the constant sound, as opposed to just using linear, where it instantly stops rising in frequency and goes to the constant frequency. That doesn't sound as realistic, so pro tip, use the exponential function. This is, as far as exactly how I'm using it, this is kind of based on the charging capacitor formula of e to the negative t over some constant. The bigger this constant is, this 2 that I'm using, the slower the windup will be. I think that's how it works. Through some experimenting, I just landed on 2 as the value that I wanted to use. And then, so it's going to wind up for 8 seconds, and then for 4 seconds, it's going to wind back down. Now, actually, now that I realize it, I'm not using the exponential on the wind down. I'm just using the logarithmic function of 1 over the time divided by this constant 6. And then, so after those 4 seconds, we wind up again. So we're using the exponential function. And then we wind down, wind up, wind down, etc. Now, a lot of this could have been a loop, I realize, but, what can I say? The goal wasn't to produce nice-looking code. It was just to get something working quickly. So, that's what happens sometimes. Now, you'll notice that each time it goes from the wind down to the wind up, it's adding this amount to the time, and that basically just compensates. It's not winding back down all the way to 0. It's only going for 4 seconds, so it's going to end up at some non-zero frequency, And by adding this to the time, we're basically jumping ahead in the wind-up function to get back to that exact same frequency that the wind-down left off on. Now, calculating what that should be, the 1.91446, I don't even remember. I think I just used my TI-89, the function solver or something. So that goes on for a while. I think it's a full 3-minute attack signal. And then finally, we get to the main function here. So it is, we're opening a file for writing, binary. It's called 2t22.raw. So it's a raw audio file, no wave header or anything. That means that when we open the file in Audacity or whatever editor we're using, we need to specify some parameters, and you'll see how that works a little later here. So, let's see. So we're seeding the random function, and then this inharm factor thing. Basically, I'm adding a little bit of inharmonicity to the sound, and that means that the harmonics are not exact integer multiples of the fundamental frequency. And now I don't, some musical instruments, like plucked stringed instruments especially, or like pianos, naturally produce some inharmonicity, and that's a big part of why they sound the way they do. A siren, on the other hand, I don't know if they actually produce any inharmonicity, but adding a little bit of it does give a certain advantage in that the relative phase between all of the harmonics is going to be changing constantly over time. And to me, this gives a little bit more of a realistic sound. Just, it keeps it, especially on the steady signal, it just keeps it from sounding, flat and sterile. Like it just gives it a little bit more of an interesting sound, even if it may not be, exactly realistic. And then, so once we calculate that, this whole section here, this loop here, this is where we're generating the actual waveform by just adding a bunch of sine waves together. Now, this is set up so that the first harmonic refers to the motor speed and not actually, the 575 or the 690, which are the main two frequencies there. So we have to keep that in mind when we are determining, which multiples of the motor speed actually end up being added to that waveform. So first of all, this 4 and 5 are basically undertones. Now, on a 2T22, the rotors have vanes on them that are, the number of vanes are less than the number of ports. So on the 10-port side, you have 5, and on the 12-port side, there's 4. And these cause very distinctive undertones in the sound that, make the siren recognizable as a 2T22 or 3T22, compared to, say, a Gents or Carter type of siren, which is also 1012 but has a very different sound. Even when you account that those are usually run on 50 hertz instead of 60. So basically, you don't want to forget the undertones. And other than that, any other frequencies below the 10th harmonic here we're ignoring. That's just going to start the loop over again. And then frequency, I don't remember what that's for. That is going to... Oh, okay, so basically the Nyquist theorem, we're at a 48 kilohertz sampling rate, so that means that any frequencies above 22 kilohertz, or 24 kilohertz, cannot exist in this file. It'll just cause aliasing. So if it's above that frequency, then we ignore it, basically. So anyway, this amplitude thing, anything multiplied by 1 is the same, doesn't change at all, so that's almost pointless. I think I must have been experimenting with that, but I just ended up on 1, so that's what happened there. Let's see here. So what is happening here is if the harmonic is above 50, we're just okay, so we're making the high harmonics drop off in amplitude a bit quicker once we get above that 50th harmonic. That's what that's doing. And okay, so this next part here, if the harmonic is evenly divisible by 10 or 12, which means we are on one of the two main frequencies, then we add it by this formula here. So we're using an amplitude of 20, and then we multiply that by the current frequency. Let's see, why am I doing that? Like I said before, I have not looked at this in a while, so... Well, anyway, this next part is... the sound that we're generating is based on a sawtooth wave, and the amplitude of the harmonics is 1 over the order of the harmonic that we're currently on. So that's what that is doing. I'm using 1.5, which actually means that the harmonics decrease in amplitude faster than they would if it was just 1 over J. That just gives a little bit smoother sound. A pure sawtooth wave is kind of harsh, so that just gets rid of some of that harshness. And then here is where we're actually generating the sine wave. The phase, now, normally, a sine wave, you generate it as a sine 2 pi ft. So it's 2 pi times the frequency times the current time in seconds. Now, you may be familiar with that formula, but it doesn't work so well in this case because the frequency f is changing, and where that 2 pi ft actually comes from is it's the integral of the frequency. Now, if you have a constant frequency, that's easy. It basically just adds the t. But if the frequency is changing, then we have to take the integral of the function that is responsible for determining that frequency. So that's where this part comes in. Since a wave file is a discrete sampled function, that makes things a little bit easier. We don't have to actually calculate the integral. We just have to, the integral is the area under the curve of the waveform. So we can basically just add together each sample value and then divide it by the delta of one sample to the next, which is just going to be 1 over the sample rate. Finally, this is where we get to adding the inharmonicity factor, which just means that we're multiplying the harmonic by a very small value, that just kind of widens the distance between each harmonic a little bit compared to where it would normally be. So again, that's generating that's making the phase between adjacent harmonics kind of get out of sync a little bit, like I said earlier. But essentially, the only thing that matters is it sounds a little bit more realistic to me, so that's why I did it. And so here at this part, I don't know if I mentioned that already, but if we're above the 50th harmonic, we're going to start to roll off the high frequencies past that point a little bit faster than what would normally happen, just by our previous definition of where the amplitude should be, the 1 over power of the harmonic, to the 1.5. And then so at this point, if it's not a multiple of 10 or 12, the next part is if it's a multiple of 4 or 5, so those are our undertones. We're going to add those, but we're going to add them at a much lower amplitude of 3 here. And then all the other harmonics are going to be added with an amplitude of 1, so much quieter than those main frequencies, which have an amplitude of 20. And then basically that's it for that loop. So this inner loop goes for the number of harmonics, and then the outer loop goes for the entire length of the file, all of the samples. And then once that's complete, then we have our completed audio file. Now, these last few parts here, so this ATAN part, the arctan function is kind of useful for generating, soft clipping distortion. That kind of goes with the inharmonicity part to, it makes the upper harmonics a little less harsh, and just overall, to me, it sounds more realistic, I guess. But yeah, that's what that is. And then we've been adding these sine waves to a double precision variable. That's what D is. However, we're writing to a wave file as a 16-bit sound, which would be a short integer. So we have to convert that to a short, and then that's what we're writing to the file. And then, once we get done with those loops, then we close the file and we're done. So, in order to run this, we have to compile it. So if you're using Linux or Mac, you probably have a C compiler already installed, either GCC or Clang or something like that. If you're using Windows, I don't have a lot of recommendations because I don't use Windows too much these days. But Visual Studio, something like that, might be the way to go. Or just look for Windows C compilers. I'm sure there's a lot of them. But anyway, let's compile this and see what happens. So, whoops, we need to include the math library because we use some of those math functions. And okay, so that gives us our executable, and running this is probably going to mess up the video because it's very CPU intensive, but let's run it and generate our file. Alright, that takes a lot longer than I thought, but we end up with this 2t22.raw file, and if I want to listen to it to see if it actually worked, we just have to go into Audacity here, and then import, make sure you go to import raw, not audio, and then select that. Okay, so this is in fact a signed 16-bit Little Endian mono and 48,000 import. Okay, that seems right. So the actual, it actually starts at 10 seconds with the wind up, so we don't need that part. That might be a little bit too much distortion for a 2T22, but sounds reasonable, I guess. So, I mean, you can kind of mess with the parameters and get a little bit more subtle effect, but right now I'm just not too concerned. So, the even though it sounds all right right now, the frequency response is going to be a little bit flat, so we need to do some work to get it to sound a little better. So a 2T22 uses conical horns, and compared to an exponential horn, the conical horn, it doesn't produce a smooth frequency response, or flat of a frequency response, but at the same time, unlike a cylindrical horn, which only produces frequencies of harmonics of a certain frequency, the 2T22 does at least, it does produce some, frequencies that are not a part of the fundamental of either the high or low tone. So we just want to keep that in mind. We don't want the frequency response to be too extreme, but we don't want it to be completely flat like it is now either. So this is probably, well, first of all, let's go into the filter curve. A lot of this is probably subjective. I mean, it isn't, but, as far as, one person might hear different things than another. So I'm just going to do this how I perceive it. But it does seem like the area where the frequency is boosted the most is right around, that 575, and which is not where I am. There we go. I'm not going to get too carried away. I'm just going to boost it by 6 decibels. Now, this would kind of make sense because, the horns on a 2T22 are larger than the STH10, and which is 12-port, and I would assume the STH10 horns are tuned to that 690 hertz, whereas the bigger horns on the 2T22, I would assume they tune them to the lower frequency, the 10-port side. I don't know that for a fact, but that would seem to be the way that you would want to do it. So anyway, we've got that boost there. It does seem like there's also a smaller boost at in the low mids around 250 hertz maybe. So I'll just add a little boost there. One of the thing, another one that I definitely hear is around 850. Again, I don't want it to be a huge boost there, but anyway. The next one would probably be the second harmonic of the high tone, so that's going to be around 1400 hertz. And I also, there's definitely a little bit of upper mid boost after that, say around 25 to 2500 hertz to 3 kilohertz, so maybe right around here. And after that, I'm not doing anything specific. We don't want the frequency response to be too flat, like I said. So I'm just adding some some stuff to make it more interesting sounding, I guess you could say. There's no rhyme or reason to what I'm doing right now. All right. So let's preview that. Seems just about right. It's probably filtering too much of the fundamental of the 12-port side. So, I don't know. Don't want too much of the high frequencies there. Alright, I'm just going to leave it at that. This isn't supposed to be perfect, but just know that almost always to get a realistic sound, you'll have to do some sort of equalization. Um, Part of the distortion is probably my laptop speakers, which aren't very good. And then, at this point, if I wanted to, I could add some reverberation. Yeah, I like that quite a lot. Um, if you're simulating this in like a city or something, obviously there's going to be a lot of buildings for the sound to echo off of, so you want a lot of reverb. I took the dampening down and the reverberance up to, just kind of emphasize that. Pre-delay, I think that's the amount of time that passes before the first echo comes in. So it should, I don't know, you just kind of have to mess with these settings until it sounds right. Okay, well, I guess that pretty much gets it to the point where, everything else can be done in the audio editor, so I guess that's all I wanted to get through for now. But like I said, at some point I want to get a little bit more detailed into all of the different advantages that there are of using additive synthesis as opposed to subtractive synthesis, and just kind of go over some techniques. Probably one video per technique, just to keep each one focused on just one topic. But I don't know. We'll see if that ends up happening and how that works. But that's all for now.